Deploying an autonomous AI agent directly into a production environment creates an immediate conflict between the model's logic and the database's requirements. This diagram maps the architectural cause. Organizations are attempting to wire probabilistic large language models directly into deterministic transactional databases, like ERPs and CRMs, from day one. That direct connection introduces data corruption risks, creates latency bottlenecks, and bypasses standard role-based access controls. These issues arise from the distinction between state and intent. Transactional databases only record state, the result of what happened. They lack the strategic rationale, the architectural trade-offs, and the human decisions that drove that result. Because language models lack the historical context behind your business processes, granting them read and write access to multi-million-dollar live systems produces highly confident, context-blind hallucinations. The strategic context these models need exists, but it walks out the door every evening at 5 p.m. The tacit knowledge held by senior architects and product managers is rarely documented. When that logic is written down, it is fragmented across disconnected systems. Slack threads, Microsoft Teams transcripts, and Confluence pages create isolated pockets of localized intelligence. To capture this history, organizations need a corporate context layer, a unified organizational memory infrastructure that aggregates these fragmented strategy documents and transcripts into a single queryable substrate. By prioritizing a document-first, forward-first approach, this system targets unstructured intent artifacts rather than structured back-end database rows. Ingesting these artifacts into a strictly read-only environment captures administrative efficiencies while maintaining a 0% blast radius for production data corruption. Traditional retrieval augmented generation relies on feeding raw wikis and documents into a model's context window. As this data volume grows, reasoning quality drops and token costs rise, creating a bottleneck known as context bloat. To solve this and accurately organize corporate intent, the data requires a rigid multi-entity knowledge graph schema. We begin with person nodes, which store SSO credentials for access control, and source artifact nodes, representing the physical files like Teams transcripts or architecture decision records. Next is the decision node, the core atomic unit of the corporate brain. This holds compressed decision statements, trade-offs, and open risks. Finally, the project node links organizational initiatives directly back to the decisions and personnel associated with them. Directed relationship edges then connect these entities, mapping human actions to strategic outcomes, showing exactly how a meeting produced a decision and how that decision impacts a project. Forcing corporate memory into this strict entity relationship map decouples reasoning from memory. It allows the AI to deliver precise, citation-backed answers, instead of vague, generalized summaries. The immediate challenge is data conversion. A 45-minute audio transcript full of filler words and crosstalk must somehow become a pristine, structured decision note. This is solved through agentic extraction, using a protocol called skill.md, a standardized markdown template utilized by an AI extraction agent. The agent applies these rules to strip away the noise. It outputs a dense markdown record containing only the key decisions made, the rationale, and action items with clear owners. The second challenge is that corporate memory evolves. If a team officially pivots to a new model in August, the AI needs a mechanism to ignore the old rules authorized in July. This requires a feature called temporal decision snapping. When a new document explicitly overrides a prior strategy, the system creates a temporal edge, labeled superseded by, connecting the old choice to the new choice. Old nodes are never deleted. Their metadata status is simply flagged as superseded, which preserves a complete audit lineage of past architectural trade-offs. This maintains a strict chronological ground truth, preventing the language model from hallucinating answers based on obsolete policy documents. Moving from graph theory to physical deployment, the Phase 1 blueprint executes this via an automated context engine running entirely at the edge. The architecture operates in 4 steps. Step 1 is the pull. To eliminate egress fees, the refined markdown summary is saved directly to object storage. The text embeddings are routed to a vector database, while strict document lineage and access control lists are secured in a relational SQL database. Step 4 is the query. An employee asks a natural language question via a Slack or web interface, passing through a single sign-on verification gateway. The query worker filters the search by that specific user's permissions, fetching the exact markdown chunks to return a grounded, explicitly cited answer. This four-step serverless pipeline creates a self-updating corporate memory bank running entirely at the edge. Evaluating these investment trade-offs requires understanding the functional boundaries of this Phase 1 edge architecture. The Phase 1 setup is purely read-only. It is bound by event-driven latency, and it cannot execute transactions or modify back-end code. This comparison matrix highlights the Phase 3 full enterprise blueprint, which bridges the gap between unstructured intent and live transactional fate. Phase 3 adds model context protocol gateways. These expose internal tools and databases to AI agents, enabling autonomous read-write actions like merging pull requests or updating customer records. It also introduces real-time change data capture. This replaces scheduled webhooks with sub-second streaming, pushing live SQL database modifications directly into the knowledge graph. Finally, it deploys trusted execution environments. These hardware-isolated enclaves allow models to process sensitive financial data without exposing raw text to host infrastructure operators. Phase 1 delivers immediate, self-funding administrative returns based on intent. Phase 3 scales that foundation into a unified intelligence graph capable of executing deterministic system mutations. Technical architecture is irrelevant without human governance. Deployment is managed by a dedicated context steering pod. This is a small, cross-functional team of product, strategy, and legal officers. They are responsible for defining source boundaries and curating the initial extraction templates. To prevent cognitive fatigue and unauthorized actions, leadership must enforce workplace comfort zones. The green zone represents unconstrained AI usage. This includes tasks like boilerplate drafting and meeting summarization that require no human approval. The yellow zone covers supervised AI usage. Tasks like specification drafting and product requirement generation demand human oversight. This enforces the explain rule. Staff must verbally explain any AI-generated architecture or strategy in their own words before executive approval is granted. The red zone prohibits autonomous action. Direct writes to production databases or handling unencrypted personal data must remain gated by human verification or API gateways. Sustainable enterprise AI depends on a governed, document-first intent layer that provides the strategic context models required to operate effectively.